So what we are trying to do, these lectures is we are trying to calculate this primordial power spectrum as predicted by inflation. And in some sense, calculating this power spectrum is like climbing Mount Everest, right? So we have a Mount Everest here, some clouds around, okay? And so far what we have done is that we managed to quantize the harmonic oscillator, which is time-dependent frequency. So we reached the base camp, right? So we have the base camp here, and that's the harmonic oscillator. So S is an integral 1/2, okay, dt 1/2 q dot square minus omega square t q square. And so we already know how to quantize this guy. So now what I would like to do today is I would like to make it to camp 2 somewhere here. So we have a camp 2 here. And that's another approximation which we'll be solving a scalar field equation on a fixed FRW background. And so quantizing this scalar field equation. And of course, if you are climbing Mount Everest, you are going up and down, and so you are training for the final ascent, right? So tomorrow we'll have the final ascent, and you'll make it hopefully to the top of the Mount Everest. So that's the plan. So here is the test scalar field equation on fixed FRW, which I'll do today. So test scalar field, so if you say the word test, it means that you don't consider the back reaction of the field on the geometry. So you just fix the geometry and you solve corresponding field equations like Klein-Gordon equation in that fixed geometry, in that fixed curve background. But you don't consider the corresponding T mu nu, which would of course change my background geometry. So that's what test means. Okay, so let's do it. So today is a quantization of test scalar field in FRW. And so of course, we could go directly to the top, right? But that would be lots of suffering and lots of and so if you do it in steps, it's much easier, and you can acclimatize to that high altitude, right? So S is now d4 of x minus 1/2. So I'll be considering just a massless scalar field. So minus 1/2 square root of minus g mu nu d mu phi d mu phi. So now if you write down this thing in the fixed FRW space, where again I'm taking the metric to be minus dt square plus a square times the Euclidean metric on E3. So this is equal to an integral of dt d3x. We have seen this already. 1/2 a cubed comes from the determinant of the metric, so it's this guy here. And then phi dot square minus 1 over a square double phi square. Okay. So that's our action. So now what is useful is to change. So this t is the coordinate t in our FRW. Sometimes, well, it is useful to change to the conformal time. So reminding you that the conformal time d eta is defined to be dt over a. So if I change this integration, it will kill. Well, it will put one more a here. But the derivatives here will be different, and this guy will be different. So if you do this change of variables, if you want, and I'll be denoting d over d eta by prime instead of dot, then your action is now d eta d3 of x and 1/2 a square phi prime square minus phi square. Okay, So this is slightly better, but still not good. So what you want to do is basically you want to canonically normalize your kinetic term. So you want to kill this a square in front of phi prime square. And the way to do it is you absorb a into phi in some sense. So you introduce a new variable, which is called Mukhanov's variable. And it's denoted by nu, and it's simply a times phi. So if you introduce this variable, then you can sort of absorb it, this a square into phi prime square. You get just 1/2 over there. And so your action now becomes d eta d3x, now 1/2, and then nu prime square minus nabla nu square plus, of course, I have to differentiate now my a, so a can actually show up in the equation, and it does, nu square, and that's it. So that's your action, which is an interesting, nice action. Okay. So far so good. We just changed the variables. We used the conformal time and changed the variables. So just a motivation. So this is not exact. I just want to motivate that. So in some sense, if you do the standard Fourier transformation to your field to nu, so I really introduce nu k, which is an integral over x, e to the I k times x, and then phi x. Then, of course, the derivative here will just become k, right? And then everything else remains the same. So well, I think I can integrate this guy by parts. So I will have nu nabla square acting on nu. So in the end, I will have k square coming out of this term if I do the Fourier transformation. So you know, Fourier transformation will give me something like d eta d3 of k 1/2, and then, well, this doesn't change, so it's nu k prime square, and then minus, and then nabla square becomes just k square, so k square minus a over a mu k square. Okay, so this would be your equation if you do a Fourier transformation as you know it, just in flat space. But this is beautiful because if you look at this thing here, it's nothing else than omega squared t, right? So you managed to actually, if this were true, you managed to transform your action to the action of harmonic oscillator with time-dependent frequency. And then the time dependence is hidden in these a double primes and a for each k. Okay, so we have like an infinite number of time-dependent harmonic oscillators. One for each k. Okay, so that's why we had to actually study the harmonic oscillator with time-dependent frequency first, and then our aim will be to really recast everything what we have here in terms of the harmonic oscillator. Okay, so how to make this more formal is that you say, well, okay, so this would be like a normal Fourier transform. So let's do exactly what we were doing is the harmonic oscillator. We said we want a solution Q, and we expand it in some basis f and f star. So let's do the same thing. So let's do nu x and eta to be now I said for each k, I have an oscillator for each k, so I will be integrating over k, d3k, and then I will have ak, uk, x and eta, and then ak dagger, uk star of x and eta. Okay, and this is precisely what we are doing in terms of f and f star. So this is some convenient solution, some basis for my solution in the Fourier space. Okay, so that's first step. Second step, we have to introduce a scalar product. And the scalar product will be exactly the same scalar product as you know it from the harmonic oscillator. But again, you have to sort of integrate over something which you don't want. Okay, so now if you have two solutions, nu1 and nu2, so the scalar product, so nu1, nu2. So now because you are talking about Klein-Gordon equation, there's always some stupid i's coming in, so it's I. And then d3 of x, and whatever you know from the harmonic oscillator. So mu1 star, and then the eta acting on both sides, and then mu2. Or any fixed time. Okay, let's not put this guy. So anyway, so this is my scalar product. So you see that this is exactly what we have, what we had before, but now we just integrate over 3x. Okay, so why not? Okay. So that's our scalar product. Now we need to impose the normalization of our basis. So this is the basis, uk and uk star. And let's impose the normalization. In terms of the harmonic oscillator, we said ff, the scalar product, is equal to 1. So now this f depends on k. Okay, so analog of 1 is delta function of k. Okay, so this is what we have. So, and impose that uk and uk prime is delta function k minus k prime. If I take the stars here, that will be -1, so it's minus delta function. And they are orthogonal, so uk prime star is equal to 0. Okay, exactly as we did yesterday, but now it's just k-dependent thing. You have to deal with the space. Okay, so far we are doing exactly what we were doing, well, yesterday. I didn't get my suitcase back. So now writing, so now we want to expand this UK, how it looks like. And for that, you remember that f had the standard form exponential I k omega t, or I omega t, when we had constant frequency, right? So basically, we'll be writing UK in the same way, but you have to think about what are the isometries of your space. So in our case, FRW has the symmetries in the spatial part of the metric, but doesn't have the time symmetry. Okay, so for that case, you can write that UK, x, and eta is equal to some normalization, 2 pi to 3/2, and then this thing here. So I can put the standard Fourier transformation in the x part because I have all the symmetries of flat space in the x part, right? But I cannot put here I eta omega or whatever because I don't have that. I don't have time symmetry. So I don't have isometry in eta, right? So but here this is okay. So this comes from the fact that we have isometries. Okay, so now the question is, so I'll take this ansatz and now I'll plug it back into the equation for the action, and then you derive the equations of motion for these things. And of course, the equations, they are interesting only in this eta part, only in the time component. So now you know everything else, but you don't know this guy, what it is. So in the end, the equation of motion coming from your action is an equation of motion for your Fk. Okay, so do it yourself, but it's obvious if you see, if you look at this, it's obvious what the result is. So then, the equation of motion gives you that Fk double prime plus k square minus a over a f of k equals to 0. This is called Muganov's equation. Everything will be named after Muganov, who did these things here. Okay, so it makes sense, right? If you look at the equation, it's precisely what you have to get, right? I know everything. I just have to solve what this guy is, and it's given. The equation of motion reduces to this thing. Yes, yes, exactly. Yeah, it's the E3 metric delta ij dxi dxj. Okay. Otherwise, if you didn't, of course, this would be more complicated, right? Yes. Okay, so we have the equation for Fk, and then it probably won't be any surprise is that if I take the scale of, so now Fk is a function of eta only. So it's basically like having that harmonic oscillator, the Q, which we had before. So there's no much surprise that if you take the old scalar product, which we defined for the harmonic oscillator, you impose out of these things that actually Fk is equal to 1, and then Fk star equal to 0, and so on, in the old scalar product for the harmonic oscillator. So without integrating d3 of x. Okay? And Fk star is minus 1. Well, there's no surprise that this is true. And in some sense, your Fk's are really the basis of the harmonic oscillator with this frequency, k square minus a double prime over a. So this is all classical. So now you want to quantize it. So again, quantization is through promoting your field to be an operator and finding the canonical momentum, and then imposing whatever new. Okay, so the canonical momentum pi is just dl over dq dot, and that becomes nu prime. So now we impose these commutation relations, and then nu and pi. So these are equal time commutation relations. So let me write it more. So I have nu x and eta and pi x prime, but the same eta, equal time commutation relations. And of course, you require that this is delta function x prime. Okay, so this is what you have. And then, again, you can show that these commutation relations are exactly equivalent to the fact that these operators ak and ak dagger now satisfy the corresponding commutation relations as you know them. So ak dagger prime is delta 3 k minus k prime, and the rest is 0. So yeah, this is the only non-trivial one. So we again have the rising and lowering operators, but now we have them for all, for many k's, right? So it's the same thing as harmonic oscillator, but now we have many more k's. Simple, right? Very simple. Okay, so now we can wipe out our Mount Everest. So now, of course, you can also define the vacuum, right? Vacuum you define as AK 0 equals to 0, now acting for all k. Okay. So now, interesting thing which you can do is the definition of the power spectrum. So I'll now just define it. But basically, what it is a two-point correlation function describing the fluctuations of your field. Okay. So power spectrum. So before I do that, so your field phi so the original field phi, which you started with, well, it's given by nu over a. Okay, so this is 1 over a, and then whatever we had for nu. So for nu we have that d3k, and then the expansion ak, and then uk x eta, which is over there. So there's 1 over 2 pi to 3/2, and then ak, fk, e not e k times x, and then plus ak dagger, fk star, e to minus e k times x. Okay, so this is your phi. So now what is the power spectrum is actually it's a two-point correlation function in the k space. So sort of phi k prime. Okay. So now this is horrible, right? So I have to Fourier transform this phi of x. So this is d3 of x, d3 of x prime, ei kx, k prime, x prime, and then the correlation function of f, x, eta, phi, x prime, and eta, and this thing here. Now I'm using some vacuum here. So now what you assume is the translational invariance of this correlation function. Well, it must be true because in x, I have all these isometries. Nothing can depend on really what the position is this one and what the position that one. Everything depends only on the difference of the two positions, right? So this guy must be translational invariant. Which means that it's a function of x and x minus x prime. And so if you use that, you can change the variables. You can change the integration also. So this is some function of x minus x prime. Now you can change the integration variables. So you call x minus x prime y. The integration measure doesn't change, and then I can integrate, over these things. So in the end, what you do get is that you kill these integrals, but you get that this is just a function of k minus k prime, or k plus k prime. So by definition, you require that this is 2 pi to the power 3, and then delta 3 k minus k plus k prime, and then the power spectrum. And this power spectrum must be a function of the magnitude of k because of the translation invariance. So p, k, and eta. So that's a definition, if you want, of the power spectrum. So this guy is the power spectrum, and it's just, you must be able to write this thing in this form if you have translation invariance. So let's show that this is the case, that you have that form. And for that, you need to suffer a little bit more. So now let's see what this guy is, and let's plug what is phi x and eta over here is, and phi x prime eta over there is. So I get two more integrals over d3 of k and d3 of k prime. Okay. So if I continue this line, this is equal to now where this, okay, 1 over a square coming from phi, and then integral d3 of x, d3 of x prime, d3 of l, d3 of l prime, and then 1 over 2 pi cube, and then al prime dagger, fl prime, ei lx, e minus I L x prime, this thing, and still I have e to the e kx and e k prime x prime. Okay, so now, of course, so what I've done here is that I'm plugging whatever stands over there, but I already deleted all the terms which cannot contribute to the vacuum. So I only left the term which has the dagger here and which has the annihilation operator here, so that it's non-trivial. All the other terms are 0. If I have AA, it just gives me 0. Or A dagger gives me 0. So this is what it is. So now you want to integrate all these things, right? So first thing you notice is that really these two things kill each other only if L prime is equal to L. Right? If L prime is not equal to L, then this simply will be 0. Right? So that's one delta function which you are getting out of that. Then integration over x and integration over x prime gives you two more delta functions.
Why is it going to be 0 if that was not L prime?
Because you have to create the same particle and annihilate it in order to get something non-trivial. If you just create, one type of particle with one momentum, these two things they give you 0. These commutation relations. I have only non-trivial things if k equals to k prime. Okay, so we have one delta function from here, two more from integrating over x and x prime, and so there's no surprise that the final result is just 1 over a square, and then this guy and that guy must be the same. So it would be 2 pi power 3 and delta 3 k plus k prime, and then fk square. Just do it yourself. It's 3 integrations to be done. Well, it's many delta functions coming out of this thing, but this is what it is. So now comparing the result of the calculation, which I haven't really done, with whatever the definition of the power spectrum is, then you conclude that your power spectrum is just fk square over a square. Okay, so we have a result that p of k is 1 over a square fk square. And that's your prescription for the power spectrum. So this is all very simple, right? So this is like an analog. When we calculated the 2-point function yesterday, all it was f absolute value square, right? So this is exactly the same result, but now it's just a function of k. So there's no surprise that this is the case, right? So we can all track all the steps which we have done yesterday is the steps which we are doing today. Okay. So now all you need to get this power spectrum is actually to find this guy here. So this guy, of course, is a solution of your Monkanov's equation, provided the right initial conditions. Right? So I need to solve Monkanov's equation, provided the right. So need to solve Monkanov's equation, provided the right initial conditions. And of course, the trick to do this is again the same one as we did yesterday. So again, you assume that in infinite past, let's say the frequency was constant, then you could actually say what the mode was. So the idea is exactly the same. So you impose an initial condition, just like the in state yesterday, initial condition. And for inflationary scenarios, it's always imposed that at early times, omega equals to constant. But it's actually even more than that. If you look at the equation for our omega, so it's k squared minus a double prime over a. So if I want this to be a constant, so k is a constant, but this guy is not. It's a function of eta, right? So I need to sort of say that this thing asymptotically goes to something. And what people say that it asymptotically goes to is actually 0. So they impose that this guy is actually vanishes at early times. Yeah, so whatever. You are not at the Big Bang. You are at the beginning of inflation. And you can play with various initial conditions, and people actually do that. But often, and the simplest possible thing is, and I will show that it realizes for some things, is that let's overdo this. So let's impose that a over a goes to 0 at early times. Okay. So if this is true, then your fk is just so now that thing is gone, and it's just a standard exponential as you know it. All right. So then fk goes to 1 over 2k e to minus I k eta at the beginning of inflation. And of course, this defines, so once I have this mode here, then this defines a preferred vacuum at the beginning of inflation. And that preferred vacuum is just AK annihilating all this vacuum. So AK on 0, provided this mode is true, equals to 0, defines a preferred vacuum and this preferred vacuum has its name, and it's not Mukhanov's vacuum, but it's different two people. It's the Bunch-Davis vacuum. Okay, so this is what people often do when they consider inflation. They just say, okay, let's see. So I need an in-state sort of coming, to my inflation thing. So in order to solve something, I probably need something like omega equal to constant. They overdo it. They just impose that this guy goes to 0. It can go to any constant, but let's say it goes to 0. Then I have this mode. This mode defines preferred AK. That preferred AK defines preferred vacuum. Okay, so this is what people do. So you have a picture, something like this. So if I have my eta, my conformal time, and then if you remember, the mode leaves the horizon. So let's say it's here. Mode leaves the horizon. And somewhere here the inflation ends, and you have the reheating, right? You have reheating somewhere here. So we'll be calculating whatever the power spectrum here is, pk, when the mode leaves the vacuum. And this happens at some time, eta, where this is sort of the mode freeze. So you know that before it enters the horizon, you have these oscillations of the mode. But once it enters the horizon, the mode freezes and stays. And then until we have the normal era, it basically stays there and waits for us. And then it transfers the energy to the plasma. And that's what we observe. Okay, so we want to calculate this pk at the time when the mode freezes, when the horizon is crossing that mode. Okay, and we do that. So we have this inflation here. But we start the inflation with this Bunch-Davis vacuum. So Bunch-Davis vacuum. That means that this is true. Okay. So that's the idea of the calculation. Of course, you may not like it, and you may argue, well, at the beginning I could have had completely different initial conditions. And the question is, if you start with different initial conditions, what is the result? Do I still get the same power spectrum? Do I still get the nice prediction which inflation gives me? And it's an ongoing research, and people write papers on these. So you can, yeah, that can be your essay if you want. Yes?
What does it mean by preferred?
Preferred.
Yes, because we have many AK.
We have many AK. So vacuum is always defined for all K, right? So I want that it's annihilated for any K. So all AKs annihilate my vacuum. But what preferred vacuum means here that really I impose that the mode behaves like this. So I really impose that this must be the initial condition before the inflation started, right? So if I didn't have that, I would have different vacuum. But yeah, this is the simplest possible you can imagine. Okay, so let's demonstrate all this machinery on some concrete example. Okay, so maybe it will become easier to understand. And let's do a prediction for the simplest possible case of inflation, which of course is not the right model for inflation because it never ends, but let's do it for de Sitter space. So let's do it for de Sitter expansion. And then we have problem with the reheating, but anyway, for inflation it's okay. And let's see what is the corresponding power spectrum. So example will be exact de Sitter. Okay. So then you know that if you have exact de Sitter, your scale factor is just an exponential where h is a constant. That's what we derived in the tutorial and whatever. So then we need to know what the conformal time is. So the conformal time is just an integral dt prime at prime. Okay, so it's just integrating an exponential, which hopefully can do. It's minus 1 over h e to minus ht. Okay, that's the, and then you can write it in terms of a if you want. So this is minus 1 over ha. So in other words, if I want to write the scale factor in terms of the conformal time, then a as a function of eta is minus 1 over eta h. And for the de Sitter space, you take that eta goes from minus infinity to infinity. Okay? So this is what it is. So now if you look at this picture here, you will impose your Bunch-Davis vacuum at eta equals to minus infinity. And the time where you'll be interested in your power spectrum is eta equal to 0. Okay, that's the end of the de Sitter. So at the end of the de Sitter, I'm interested in the power spectrum. Okay. So now, what is your Mukhanov's equation now? Still written here. So this is your Mukhanov's equation. So you can calculate what A double prime over A is, right? And plug the result there. Okay, so that's very simple. So Mukhanov's equation is 0 equals to fk double prime, and then plus k square. And then if you calculate A double prime over A, it's just minus 2 over eta square using this type. Here, h is a constant, fk. So in this case, this is your omega square. Right? And then this omega square has that nice property that really A double prime over A goes to 0. So it actually satisfies that initial condition over there. Because if eta goes to minus infinity, this term disappears. And I really have omega equal to k. So this thing really has the Bunch-Davis vacuum. Okay, we have Bunch-Davis vacuum as eta goes to minus infinity. So our mode of, so limit eta goes to minus infinity of fk must be whatever we prescribed there, square root of 2k I k eta. So all you have to do is solve this equation provided this initial condition. And then you know the power spectrum. Okay?
So the result is independent of h?
Well, let's wait for the result. All right, so the solution of this equation can be found if you use your Mathematica or Maple or whatever. It actually gives you, provided this is your initial condition, it gives you the solution, and the solution is called Bunch-Davis mode function. So, okay, so fk, the solution is fk equals to 1 over square root of 2k e minus I k eta, and then 1 minus I over k eta. Okay? It's Bunch-Davis mode function. And you can easily realize that when eta goes to minus infinity, this term is gone, and really I satisfy my initial condition. But you can also plug back into the equation and verify that it's satisfied. Okay, so this is the solution. So now if you want the power spectrum, it's just fk square over a square. So now, of course, a square contains this h, right? So the h enters through the a square. Okay, so a is 1 over eta h square, so we have 1 over a square, so this is equal to eta square h square, and then whatever we have here, so this is a modulus of fk, so this thing disappears and this thing remains. So 1 over 2k, and then you are taking this complex conjugate thing, and that gives you 1 plus 1 over k square eta square. Okay, And now you are interested in this power spectrum at the time when the inflation ends. So at the time when eta goes to 0. Okay, so this thing equals to eta goes to 0. So the limit, okay, so this guy goes to 0. This guy will blow up, but they fortunately cancel. So it's just this thing plus that thing. And it's equal to h squared to k cubed. Okay. And this is a famous result. Very, very famous result. So that's your power spectrum in the de Sitter space. In other words, if the inflation would last forever, basically. So now this is a famous scale invariant power spectrum. Scale well, in some sense, de Sitter space has no scale, so this thing must be scale invariant. But let's convince you that this is really scale invariant. So, well, obviously depends on k cube. So why do I call this guy a scale invariant power spectrum? Okay, so for that, let's show you a little calculation that this is really scale invariant. So now we are doing advanced conformal field theory, right? So why is this y scale invariant? Okay, so let's consider a scaling transformation. So let's consider I have a field of x, and now I scale this x. So I go from phi of x to phi lambda of x. Okay, so or infinitesimally, well, I can put lambda is equal to 1 plus epsilon and do a Taylor expansion on that. So, and then you find that delta phi is just x dot d phi over dx. Okay, so that's your infinitesimal transformation, infinitesimal scaling transformation. Just do the Taylor expansion to the first order. Okay, so this is a scaling transformation. Scaling transformation. So now, of course, what you require, if you have scale invariant theory, then your correlation functions must be scale invariant. So let's look at the 2-point function. Okay, so scale invariant theory, then the 2-point function is scale invariant. So what it means is that if I do that infinitesimal scaling thing on my 2-point function, I have to have 0, so x d over dx, and now it will be acting on a 2-point function phi x phi y, but why not to take phi y equal to 0? So phi x and then phi 0, this thing must be true. So if my theory is scale invariant, then the 2-point function must be scale invariant, and so this must be true. Okay, so what is this? Well, it's pain. So let's write this in terms of the momentum space. Okay, so I write f phi x in terms of the momentum space, f phi 0 in terms of the momentum space. So it'll be two integrals. So this is x dot d over dx, and then I have two integrals, d3k, 2 pi 3, and d3k prime, 2 pi 3, and then e minus I kx and then I would have ky, but that because y is 0, I have 0, well, 1 times 1, and then phi k prime. Okay. So now if you look at the definition of the power spectrum, it's precisely that correlator between phi k and phi k prime. It gives you pk, and then some factors. So this thing here is 2 pi cube delta k plus k prime, and then pk. Okay. So that means I can actually I can kill one of the delta functions, one of the integrations by using this delta function. So let's kill the k prime integration. So this is equal to x dot d over dx integral d3k 2 pi cube, and then e minus I kx, and then pk. Okay, I killed one of the integrations. And now we use the delta trick. So if you look at this thing, so if I can pull these guys into the integral, right? So this is just over k. So what it is that this thing actually picks my k down. So all it does is I have x dot k inside the integral. Okay. So now the delta trick is to change this integration, the derivative with respect to x, to derivative with respect to k.
But the integral doesn't converge because p was like 1 over k cubed. So it's like a logarithmic divergence, right? It was like
P over k cube. So it doesn't.
Is that correct,
No, but you are picking one more. Oh, you are picking one more k. Okay, let's look into that later. Symbolic operations, right? So, okay, if that are true, I couldn't do what I'm doing, but it must be true. So you take pk to be, well, you regularize it, right? You can put 3 and then power something so that it's regular, and that's fine. Okay, so the delta trick here is to really change the derivative with respect to x, the derivative with respect to k. So this is an integral, d3k, 2 pi cube, and then I put minus d over dk, acting on e to minus I k dot x, and then dot k, and then pk. Okay, if you look at that, really this thing just brings me down x. I will have x dot k, and I have exactly what I had before. Okay, so this is the delta trick. Now we can integrate by parts. So moving this derivative from k to the derivative of these two things. So you will have a derivative of k with respect to k, which is something like 1. But it's a divergence, so it actually gives you 3. And then the other derivative will be acting on this guy here. Okay, so this is equal to an integral d3k 2 pi cube e to minus I k dot x. And then divergence of k gives you 3. And you have plus k dot d over dk, and then pk. Okay, so we're done with the cheating. So we have 0 equals to this. Of course, it means that this guy must be 0. So you have an equation for pk. You know that 3 plus k dot d over dk acting on pk is a differential equation for pk, must be equal to 0. And the solution is pk equals to 1 over k cube. Okay, so from here, and maybe I'm cheating here, but that's okay. It's proportional to 1 over k cube. So indeed, if you have scale invariant theory, meaning that under infinitesimal scaling transformations, your 2-point function doesn't change, then your power spectrum must go like 1 over k cube. That's why this power spectrum is called scale invariant power spectrum. Okay. And then yeah, we can worry about the convergence of the integral if you want to. Okay. So the last thing I want to do is to introduce something which is used in cosmology, and that's the spectral index. So our calculation established that for exact de Sitter space, you have power spectrum which is scale invariant, which goes like 1 over k cube. But if you have some departure from de Sitter space, if you have real inflation, then it won't be exactly true. It won't be exactly 1 over k cube. And the way to parameterize that is through the spectral index. So spectral index. Ns is equal to 1 plus k d over dk. That's a definition. Log of k cube pk. Okay. So this is a definition of the spectral index. So of course, if pk goes like k cube, 1 over k cube, this is just 0. Derivative gives you 0. Well, or whatever constant gives you 0. So ns is equal to 1. Okay, so ns equals to, now, if it's equal to 1 exactly, then you say scale invariant spectrum. If it's less than 1, then you say that the spectrum is red tilted. And if it's bigger than 1, then you say it's blue tilted. Okay, just a definition. So now interesting thing, well, okay. So if n_ns equals to a constant, then you can easily integrate this equation. So if this guy is constant, I can find what my pk is. Okay, I just put this guy, that's -1 on the other side, divide by k, which is d over d logarithm of k, and then put these things in. So then your solution is that pk is equal to, or is proportional to, k to -3 plus ns -1. Okay, if ns equals to constant, you can just solve this equation, and this is your solution. pk is proportional to this thing here. If ns is not equal to constant, meaning it depends on k, then you are in bigger trouble. But just the terminology, you would say that you have running spectral index. And basically what it means is that your power spectrum is not, cannot be written as a polynomial of to some power. Okay, so you have running spectral index. So now what is the observation? So it is observed that it is a constant, plus minus, and it's actually red tilted. So observation gives that ns is 0.96 plus minus 0.01. And that it is a constant, right? But this is just what it is. So it's red tilted. Okay, so now you see, I will discuss tomorrow the cosmological parameters. But basically, cosmological parameters, everything that characterizes our universe as we know it, is characterized by 6 basic parameters. 3 of them are nothing else than the densities of your matter component. So how much you have dark energy, how much you have dark matter, how much you have baryons. So it's enough to have 3 numbers to actually say what the history of the homogeneous universe is. 2 additional parameters describe your primordial fluctuations. One of them is ns. The other one is we established that if ns is equal to constant, then pk is equal to that, right? So, but I can write it as pk at some given k0. So this will be given by some amplitude of this pk at k0, and then I'll put k over k0 and whatever I established over there. -3 plus ns minus 1. Okay, so this you can do. So now this is the amplitude of primordial fluctuation. And that's your another parameter which characterizes the universe. Okay, so you have 3 matter densities. You have the spectral index, and you have how big the primordial fluctuations were. These are 2 more parameters. They characterize the initial fluctuations. And there's one more parameter, which is called reionization. And I will not discuss it, but it's basically what happens is that after everything is recombined into hydrogen and helium, which are neutral, then once you form stars, these stars start emitting, high energetic photons or whatever, and they reionize your hydrogen again. And so this thing is characterized by optical depth. So how far a photon can travel until it meets the charged thing, which destroys it, right? And so that's the last 6 parameter of the universe. So now you know all the parameters which characterize our universe. 2 of them, primordial fluctuations, this guy and that guy, the 3 matter densities, and then how much actually the plasma is not neutral. Okay, so let me stop here and let me do the final climb to the top tomorrow.